Hi, we're going to talk about the material from Lecture 9. Lecture 9 is more stuff about probability, a bunch of topics that advance our study of probability a bit. As usual, I want to say that watching these videos is no substitute for reading the book or notes. You still have to do that. Okay, first topic is the complement of an event. You remember, if you have an event E, it's a subset of the sample space. It contains some outcomes, and let's just draw a picture. Here's E, right? This is the sample space, and then we'll draw a little circle for E. And E will contain some outcomes, like the x1, x2. Maybe it contains x4. And over here, this is x3 and x5 and x6. E contains x1, x2, and x4. E is a subset of the sample space that contains some outcomes. Also, if you take E out of here, what's left over is also a subset of the sample space that contains some outcomes. And that subset is called the complement of E. The complement of E, and it's just the event, the subset that contains all the outcomes that are not in E. Right? The notation for it is E complement, E with a little c superscribed. So here, E in this picture, E would be the set containing x1, x2, and x4. And E complement would be the event, the subset containing x3, x5, and x6. Now, notice that E and E complement never overlap. Right? They never overlap because E complement is just everything outside E. Also, every outcome is in one of these two, either in E or in E complement. So E and E complement together contain all the outcomes in the sample space with no overlap. And what that means is that the probability of E plus the probability of E complement has to be the probability of the whole sample space, which is 1. And that gives you a little formula for the probability of E complement. The probability of E complement is just 1 minus the probability of E. Also, of course, the probability of E is 1 minus the probability of E complement. How about this? What is the complement of E complement? That would be the set of all the outcomes that are not in E complement. If you look at the picture here, it's pretty clear what that is. The set of all the outcomes that are not in E complement is exactly E. So the complement of E complement is just E. Okay, let's see a little example here. A fair die is thrown. If E is the event, you get a number less than 3. What is E complement? What is the probability of E complement? Well, first of all, let's write out what E is in terms of outcomes. E is the event you get a number less than 3, so that is you get a 1 or a 2. We're assuming a 6-sided die here with the normal numbering and everything. Okay? And so E complement is just an event, right, a subset of the sample space that contains all the outcomes not in E. So this would contain 3, 4, 5, and 6. Well, now it's pretty easy to do this part. The probability of E, of course, is just 2 out of 6 because it contains 2 of the equally likely outcomes, and there are 6 of those altogether. And the probability of E complement would just be 4 out of 6. And of course, if you add those together, you get 1. Okay, next topic is the intersection of events. Let me draw a picture here. You may be used to the idea of intersection of sets. Here's a little Venn diagram. Let's say this is the event E, and this is the event F. This little area in the middle here, right, remember, E, the circle represents E, it contains all the points inside the circle. So this point in particular is in E. In F, over in F, all these points are in F. some of those points are in both. And that is the intersection. All the points that are in both, that's the intersection. So the word is intersection, the intersection of E and F. That is just the set of all outcomes that are in both E and in F. This is all written out in the book and notes, so I won't write it here. But the notation for it is E with the little upside down U thing, F. E intersect F. Notice that a point, let's say an outcome, is in E intersect F if and only if it is in E and in F. And that means that the probability of E intersect F really is the same as the probability of E and F. The intersection corresponds to and. If you think in terms of events occurring or not, the probability that E intersect F occurs is the probability that E occurs and F occurs. The probability that both events occur. And the only way that can happen is if you do the experiment and you actually end up with an outcome that's in both sets, because that's what makes an event occur. Right? The experiment is done and the outcome is actually in the event. So for them both to occur, you'd need to have the outcome in E and in F. Okay, next little topic, let's do this, is the union of two events. And once again, the picture is useful. And here's the event E, here's the event F. The union of E and F is the set of all outcomes that are in E or in F or in both. If they're in both, well, then they're in E and they're in F, so we can consider them to be in either one. So this is the union of E and F, and the notation is E with a U and then F. E union F. Notice that an outcome gets to be in E union F if it's in E, or it's in F, or it's in both. So the probability of E union F really is the probability of E or F. Excuse me. How does E union F occur? It occurs if the outcome is in E or in F or in both. And so probability of E union F is just probability of E or F, where it is understood that or means E or F or both. Okay, we're going to try to develop a formula for the probability of a union, probability of E union F, in terms of the probability of E and F that we begin with. And we're going to do that looking at this example right here. This is a picture of two events, E and F, and some outcomes, numbers 1, 2, 3, 4, and so on. Outcomes 1, 2, 3, 4, 5 are in E. Outcomes 4, 5, 6, 7, 8, 9 are in F. And then there's an outcome number 10 that is outside both E and F. Now here's the thing. The first thing you might try to get a formula for the probability of E union F is you might try just probability of E plus the probability of F. But that's going to be a problem. Think of all these outcomes as being equally likely. Then the probability of E, there are 10 outcomes altogether, so the probability of E would be 5 out of 10, because 5 of the outcomes are in E. The probability of F would be 6 out of 10, because there are 6 outcomes in F. But if I add those two, I've counted the probabilities of these two outcomes twice. Right? Whatever is in the intersection, I count twice when I just add the probability of E and the probability of F. So if I want a general formula for the probability of E union F, I'll have to take the probability of E plus the probability of F and subtract the probability of E intersect F. That's the formula. This is sometimes called the addition rule for probability. The probability of E union F is probability of E plus the probability of F minus the probability of E intersect F. So here's one where we can actually get numbers. We're going to roll a single die, so we all know what the sample space is there. And let E be the event that you get a number less than 4. So what would that be? That would be the event 1, 2, 3. And F is the event that you get an odd number. So F is the event 1, 3, 5. So what's the probability of E union F? I want to do this two different ways. First, I can compute this directly in this case. E union F contains all the outcomes that are in E or in F or in both. So that would be 1, 2, 3, and 5. All the outcomes here are equally likely, and there are 6 of them. So that says the probability of E union F is 4/6. Okay, here's a second solution using the formula. The probability of E union F is probability of E plus probability of F minus the probability of E intersect F. Well, let's just go off over here somewhere. Let's go here, and we'll compute E intersect F. That's going to be the set of all outcomes that are in both E and F. 1 is in both, and 3 is in both, and that's all. So E intersect F is going to be just the event containing the outcomes 1 and 3. So here, these are easy. The probability of E, there are 3 outcomes in E, 6 altogether, everything equally likely. Same with F, 3/6. And now the probability of E intersect F, that contains 2 outcomes out of the 6 equally likely outcomes. So that's 2/6. So when you do the arithmetic here, you end up with 4/6. It's the same thing you ended up with over there, of course. Okay, let me give you a definition. 2 events, E and F, are mutually exclusive if E intersect F is the empty set. In plain English, E and F are mutually exclusive if they have no outcomes in common. There's nothing that's in both E and in F. Of course, this means that if you do the experiment, right, one trial of the experiment, then it is only possible for E to occur or F to occur, or neither, but you can't have them both occurring. Because again, the only way an event occurs is if you do the experiment and the outcome of the experiment is actually in that event. And this means that there are no outcomes that are in both E and F, so E and F cannot both occur on one trial of the experiment. That's usually the key to figuring out whether or not 2 events, usually described in a problem, are mutually exclusive. Right? You think to yourself, well now, is there any outcome of the experiment? If I do the experiment, is there any outcome that could make both of those events happen? So that's what would be necessary. So let's do a couple of little problems here. This tends to be a little difficult, so we want to do several little problems. Okay, first experiment, roll a single die. Let E be get an even number. Let F be get an odd number. Are those 2 mutually exclusive? Well, is there any outcome that could make them both occur? Is there any outcome that could make E occur, that is, that would be an even number, and would make F occur, so it would have to be an odd number? Clearly there is not, right? So the answer to this is yes. We could actually write this out. In this case, E would be 2, 4, 6. F would be 1, 3, 5. Right? And it's pretty obvious that E intersect F has nothing in it. Right? There are no outcomes in E intersect F. So they are mutually exclusive. Okay, second experiment, same as the first, roll a single die, but now we're going to let EB get an even number and FB get a number greater than 3. So that is a 4, 5, or 6. Are these two mutually exclusive? Again, this is a very simple problem, but ask yourself, is there any outcome of that experiment, of the experiment of rolling a single die, that could make E occur and F occur? If there is any outcome that could do it, they're not mutually exclusive. So is there any outcome of rolling a single die that would give you both an even number and a number greater than 3? Sure, right? The outcome 4 would make both of these occur. It would be an even number, so E occurred, and it would be a number greater than 3, so F occurred. So these are not mutually exclusive, and if you wrote out the sets, you would find that they did have a non-empty intersection. Okay, here's a third one. We're going to flip a coin 3 times, and we're going to define 3 events here. E is the event you get at least 2 heads, F is the event you get all tails, and G is the event that you get at least one of each. I wrote kind of a bad description of that here. I want to replace it. Which pairs of events are mutually exclusive? So, first of all, what are the possible pairs of events? E and F is one pair of events, E and G is another, and F and G, right? And there aren't any others. So we're just going to consider these pairs one at a time. How about E and F? Are they mutually exclusive? E is you get at least 2 heads, and F is you get all tails. Well, those are clearly mutually exclusive, right? I mean, if you get all tails, then you didn't get any heads, so E could not have occurred. Going the other way, if E occurred, you got at least 2 heads, so you certainly didn't get all tails. So those two rule each other out. They are mutually exclusive. How about E and G? You get at least 2 heads, and you get at least 1 head and 1 tail. Those are not mutually exclusive. Here is an outcome that could make them both happen. Heads, heads, tails. This makes E happen because you get at least 2 heads. This means heads on the first flip, heads on the second, tails on the third, right? You get at least 2 heads, and you get at least 1 of each, so G happened. Those are not mutually exclusive. How about F and G? Get all tails and get at least 1 of each? Well, those are mutually exclusive for the same reason that these two are. If you get all tails, you certainly did not get any heads, so you couldn't have gotten at least 1 of each, and vice versa. Okay. Let me mention something about mutually exclusive events and the addition rule. Remember, the addition rule is the probability of E union F is probability of E plus the probability of F minus the probability of E intersect F. Okay. If E and F are mutually exclusive, then E intersect F is empty, and this is 0. And so for mutually exclusive sets, it is true that the probability of E union F is just the sum of the probabilities of E and F. Okay. One more topic, the last one in this section, contingency tables. A contingency table, this is a particular two-way contingency table, so-called because there are 2 rows and 2 columns. This particular one shows the results that were found when researchers examined a possible link between a specific gene and a high IQ. They tested a bunch of children to see if they had a specific gene, and also they gave them an IQ test to see how high their IQs were. And you can see if a person had a high IQ, he's identified in this row. If he didn't, it's in this row. And similarly with the columns, people with the gene were put here and people without the gene here. Okay, so it turns out the total here is 52. That means there were 52 people with high IQs and 50 people whose IQs were not considered high. And so there must have been a total of 102 people altogether. Similarly, 72 had the gene and 30 didn't, and these numbers also add to 102, and of course they have to. Right? And that also means that there were 102 people in this study altogether. Okay, first thing is, what is the sample space of this experiment? Right? Well, the sample space contains all the possible outcomes. The possible outcomes are the child had a high IQ and the gene. The child had a high IQ but didn't have the gene. That's 2. The child did not have a high IQ but did have the gene, and did not have a high IQ and did not have the gene. There are 4 possible outcomes, and we write them this way. Right? IQ high, gene found, IQ high, gene not found, and so on. And this is the only kind of this kind of contingency table setup is the only time you will see sample spaces written this way in this course. They're pretty easy to identify in problems. All right, so let's do some calculations from this table. Here's the idea. You're going to choose a child at random from the 102 children who were studied. First question, what is the probability that that randomly chosen child had the gene? Okay, well, the gene was found in 72 of the children. There were 102 tested altogether. So the empirical probability is the number of times the event had the gene was observed divided by the size of the number of observations, the size of the sample studied. So the probability here is 72 out of 102. What is the probability the child does not have a high IQ, meaning the randomly chosen child? 50 children out of 102 did not have the high IQ, so that's 50 over 102. What is the probability that the child has both the gene and a high IQ? So it has the gene and a high IQ. Well, if you had the gene, you were in this column. If you have a high IQ, you're in this row. So it's those 33 right there. The probability, if you choose somebody at random from this study, that that person has both the gene and a high IQ was 33 out of 102. And finally, here's one that requires more thought. Let's find the probability that the child does not have the gene or does not have a high IQ. Okay, this one takes a little more doing, so I'm going to go ahead and write out. Let me just fold this down so we can see it. I hope. All right. Give me a place to write and you a place to see. So let's define a couple of events here. We're going to let E be the event does not have the gene. And we'll let F be the event does not have a high IQ. All right. And we want the probability of E union F, the probability that the child does not have the gene or does not have a high IQ. Well, we're going to go by the formula here. The probability of E union F is the probability of E plus the probability of F minus the probability of E intersect F. So I need these probabilities, and they're actually pretty easy to get. The probability of E is the probability that the child does not have the gene. Right? 30 people did not have the gene out of the 102 tested. So this is going to be 30 out of 102. F is the event does not have a high IQ. 50 out of 102 did not have a high IQ. And finally, E intersect F is the event that you don't have the gene and you don't have a high IQ. And that would be the people right here, these 11 people. They didn't have the gene and they didn't have a high IQ. So the probability of selecting one of them is 11 out of 102. And if you add these together, you get 69 out of 102. That's the probability that the randomly chosen child from this study does not have the gene or does not have a high IQ. Alrighty, thanks for listening.